Right now, the largest and most expensive stadiums in US history are rising from the ground, and they're unlike anything we've seen before. From futuristic arenas packed with new features to record-breaking capacity, these projects are redefining sports and entertainment. In this video, we're revealing the biggest stadiums currently under construction across America in 2025. Unlike traditional stadiums that often feature concentric ring designs, the new Nissan Stadium, slated for completion in 2027, relies on a sweeping, asymmetrical configuration that responds to both the topography of the site and the orientation of surrounding city infrastructure. Located along the east bank of the Cumberland River, the stadium's footprint had to be carefully integrated with adjacent roads, bridges, and floodplain zones, which dictated early-stage decisions in earthworks and utility planning. Before vertical construction could even begin, site crews carried out a multi-phase ground improvement process that included dynamic compaction, surcharge loading, and the installation of wick drains to accelerate settlement. Structural work begins with a deep foundation system of drilled shafts socketed into bedrock. These shafts support a vast network of grade beams and pile caps that distribute vertical loads from the seating bowl, club levels, and roof system. Unlike traditional column layouts, this stadium uses staggered grids and variable bay widths to accommodate multiple functions: open concourses, press decks, and premium seating tiers. Concrete work is executed in sequence, with forming systems tailored to curved walls and sloped decks. Tower cranes positioned along the stadium's perimeter lift formwork, rebar bundles, and pre-tied mesh into place with logistical precision. The steel superstructure, meanwhile, is assembled from massive box girders and diagonal bracing members that define the profile of the upper seating bowl and roof. Truss segments arrive in prefabricated units from regional steel fabricators and are assembled on temporary shoring towers before final welding and bolting. Some of the longest cantilever trusses extend more than 200 feet over the seating area to support the edge of the canopy roof. These trusses transfer loads to reinforced concrete cores that double as vertical circulation towers. MEP systems are routed through centralized distribution corridors. Primary HVAC units are suspended in mechanical penthouses built into the roof structure, with chilled water and air supply lines running through steel grating walkways and vertical shafts. Electrical rooms feature dual-feed switchgear to ensure uninterrupted power delivery, especially during nationally televised events. Thousands of linear feet of low-voltage conduit are embedded in the seating risers to support seat-integrated lighting, power, and data ports. The stadium's roof is a major architectural and engineering focal point. Constructed from a combination of structural steel, cable tension systems, and ETFE membrane panels, it provides weather protection to over 2/3 of the seating bowl while remaining open over the playing field. Drainage from the roof is managed through concealed scuppers and high-capacity downspouts that feed into an underground stormwater retention system. Roof erection requires hydraulic strand jacks, temporary falsework, and real-time surveying to ensure millimeter-level accuracy during the tensioning process. Interior finishes will be applied in a final phase that includes terrazzo concourse flooring, steel mesh guardrails, and modular wall systems for suites and hospitality areas. Fire protection systems include both wet pipe and pre-action sprinkler configurations, with standpipes running through all stairwells and cores. As 2027 approaches, commissioning teams will systematically test building systems, conduct life safety inspections, and finalize documentation for occupancy certification, ushering in the full operational readiness of the new Nissan Stadium. Starting with mechanical systems rather than foundations, the new Commander Stadium, scheduled for completion in 2028, will feature a complex network of distributed HVAC units, substation vaults, and emergency backup systems arranged around a high redundancy operations core. Unlike traditional central plant configurations, this stadium will utilize multiple mechanical mezzanines at various elevations, each linked by vertical chases running through the structural cores. These shafts will carry chilled water piping, variable air volume ducts, electrical busways, and fiber optic trunk lines. Heat and ventilation loads are carefully modeled for Washington's humid summers and cooler winters, and the stadium will incorporate both active and passive conditioning strategies, including thermally broken curtain wall assemblies and reflective rooftop surfaces. The foundation system is planned around a combination of driven precast, concrete piles, and drilled shafts, determined by subsurface variability across the large urban site. Prior to deep foundation work, the project team will need to execute extensive ground densification, as portions of the site lie in geologically loose soil conditions with historical fill. Where underground utilities intersect with the structural grid, pile caps will be reconfigured with built-in blockouts and ducts, enabling uninterrupted service routes. As the structural frame takes shape, the stadium will begin rising through a combination of cast-in-place concrete and structural steel. Core walls housing stairwells and elevators will be slip-formed in vertical stages, allowing reinforcement and embedded items to be installed continuously. Around these cores, steel raker beams will support precast seating elements, which are manufactured off-site and delivered in just-in-time deliveries. Each seating module includes cast-in embeds for railing systems, electrical conduit, and mounting brackets for digital displays. The stadium's exterior will feature a hybrid cladding system with aluminum composite panels, glazed sections, and ventilated rain screens. A unique vertical louver system will provide both shading and a dynamic visual profile that changes depending on the viewer's angle. These louvers are to be attached to a secondary steel frame mounted onto the primary structure using thermally isolated clips to prevent cold bridging. LED lighting strips and dynamic signage will be integrated into the facade, creating a programmable canvas for team branding and event-specific visuals. Above the bowl, a lightweight roof canopy is to be suspended from a cable-supported compression ring, offering broad shelter without enclosing the stadium. The structure relies on massive masts around the perimeter, each post tensioned into deep caissons. The roof surface itself will be constructed using a layered ETFE system with fritted coatings to control daylight penetration. Integrated gutters and scuppers will route stormwater to perimeter cisterns designed for reuse in irrigation and maintenance. Beneath the playing field, an array of hydronic tubing, drainage aggregate, and geofoam layers will create a fully conditioned surface that can withstand year-round use. Perimeter tunnels will provide access for maintenance and security personnel, while utility trenches will house lighting control lines, camera cabling, and telecommunications networks. Instead of beginning with earthwork or steel, it's the structural interface between public concourses and premium zones that will stand out as a complex undertaking in the new Chicago Bears Stadium, which is planned for completion in 2027. Designed to be a multi-tiered facility with broad circulation paths and dedicated vertical access cores, the stadium will employ a tiered structural scheme to separate general admission, club level, and suite access into distinct vertical zones. This requires a dense network of stairwells, escalators, and elevators, all stacked in alignment with structural walls that also serve as lateral shear components. Moving down to the field level, the playing surface will be built on a multi-layered engineered base. A compacted subgrade of aggregate material will be topped by a network of subsurface drainage pipes laid in herringbone pattern. Above this, heating coils will be embedded in a concrete slab to provide winter conditioning, followed by engineered sand layers and the natural grass root zone. The perimeter includes trench drains and access vaults to manage both water removal and field utility service points. The stadium will feature a continuous seating bowl built from precast components tied into a poured-in-place concrete frame. The lower bowl will nest into the grade with retaining walls constructed early in the sequencing, allowing the earth to resist lateral loads and form a thermal mass. Above this, a steel-framed superstructure will support mid-bowl and upper-tier seating. Raker beams and cross-bracing will provide load transfer into deep foundations, which consist of drilled caissons extending to bedrock depths, necessary to combat frost heave and soil variability. Rather than building out roof structures at the final stage, this project will prioritize the canopy system earlier than typical. This is due to the use of integrated trusses that tie into upper concourse slabs, making the canopy part of the building's lateral stability system. It will consist of long-span steel trusses prefabricated off-site and craned into position using tandem lifts. Purlins and decking will support a roof skin composed of polycarbonate panels with integrated solar collection cells, adding resilience and contributing to energy offset goals. Mechanical systems will be distributed through mechanical mezzanines located between the upper decks and suite levels. Variable air volume units, hot water heating loops, and chilled beams will condition enclosed interior spaces. Open air concourses will be supported by displacement ventilation in enclosed service areas and radiant heating panels positioned under overhangs. Electrical infrastructure includes a central substation feeding redundant switchgear with additional UPS units designated for mission-critical systems such as lighting controls, security networks, and the scoreboard array. The exterior of the stadium will blend glass curtain walls, steel cladding, and stone masonry. Materials selected to echo both the historic civic buildings of Chicago and the city's modern architectural identity. A pedestrian plaza with integrated snow melt tubing will surround the stadium, channeling foot traffic through access-controlled entry gates aligned with structural grid lines. With all systems scheduled for commissioning by the second quarter of 2027, final testing, inspection, and certification will pave the way for the Bears to open their new stadium that fall, fully compliant with NFL standards and poised for multi-use flexibility in future decades. Beginning with vertical transportation systems, the new EverBank Stadium, projected for completion in 2028, will integrate an expanded array of elevators, escalators, and accessible ramps that are designed around a radial grid structure. Each of the stadium's core towers will house multiple vertical circulation shafts embedded into reinforced concrete shear walls that also provide the lateral stiffness necessary to withstand hurricane-level wind events common to Florida. These towers will not only support fan movement across multiple levels, but also serve as service corridors for mechanical systems, egress stairs, and emergency response paths. Descending to the foundations, the stadium will be built atop a substructure that accounts for both soft coastal soils and proximity to the St. Johns River. Engineers will employ a pile-supported mat foundation, combining steel H-piles driven to refusal with cast-in-place concrete caps and a continuous grade beam network. This system distributes both dead and live loads from the stadium structure, while minimizing differential settlement across the wide footprint. Prior to foundation work, a ground improvement program involving surcharge loading and wick drains will be executed to consolidate moisture-laden soils and speed up the settlement curve. As the main seating bowl is constructed, precast concrete modules will be staged off-site and delivered in sequenced shipments to be lifted by tower cranes into steel raker beams. These rakers will be bolted to cast-in-place support walls with embedded anchor plates and tension bolts. Each seating section will include cast-in penetrations for MEP stub-outs, lighting, and railing systems, reducing the need for secondary coring post-installation. The upper deck, designed to cantilever over the lower levels without obstructing views, will rest on long-span trusses that extend inward from perimeter support columns anchored in massive pier footings. Overhead, the partial canopy will be built from a network of curved steel girders arranged in an outward-leaning ring supported by inclined columns. The roof surface will feature tensioned PTFE fabric panels treated for UV and rain resistance, allowing diffused daylight while shielding fans from the elements. Integrated into the roof's edge will be high-capacity gutter systems and downspouts connected to underground stormwater retention tanks sized to accommodate peak rainfall events, typical to Jacksonville's climate. Mechanical and electrical systems will be divided into north and south zones, each with dedicated plant rooms housing chillers, air handlers, switchgear, and backup generators. HVAC supply and return will be routed through steel-framed duct risers, while electrical conduit will follow parallel chases with thermal isolation to prevent overheating. Data infrastructure will be supported by multiple MDF and IDF rooms, each linked by redundant fiber lines to ensure seamless connectivity during events. The field system will incorporate natural Bermuda grass underlain by a heated subslab and vacuum drainage matrix. Below the root zone, temperature sensors and moisture probes will feed into a digital control system that adjusts irrigation and heating to maintain optimal growing conditions. The field perimeter will include recessed broadcast cable trays, camera mounts, and access ports for maintenance vehicles. With an official stadium opening targeted for the 2028 NFL season, final systems commissioning and occupancy certification are expected to wrap up in late summer of that year. Upon completion, the new EverBank Stadium will not only replace its predecessor, but redefine how an open-air venue performs in a subtropical urban environment. Rather than focusing first on steel or foundations, the new Highmark Stadium, anticipated for completion in 2026, will distinguish itself through its climate-adapted design, shaped heavily by Buffalo's lake effect weather patterns and winter wind exposure. The entire project will be engineered with cold performance in mind, incorporating windbreak barriers, thermal zones, and strategically placed radiant heating elements throughout concourses, seating zones, and critical access points. Construction begins with site stabilization, which is critical due to historical fill and the seasonal freeze-thaw cycles in western New York. The earthwork scope includes excavation down to undisturbed subgrade, followed by layered backfill compacted in lifts. Foundations are primarily comprised of drilled shafts and reinforced concrete-grade beams, forming a grid beneath the stadium's structural core. Below-grade waterproofing membranes and under-drained systems are installed early to protect foundation elements from groundwater intrusion and ensure long-term durability. As superstructure work proceeds, cast-in-place cores rise first. These serve not only as the vertical circulation routes for fans, but also house major MEP infrastructure, fireproof stairwells, and elevator banks. Around these, a structural steel frame is erected using crawler cranes and modular steel assemblies. The framing system supports two major seating tiers, with mid-bowl premium areas cantilevered to preserve unobstructed sightlines. Seating decks are constructed using precast treads and risers with integrated embeds for power, data, and safety railing systems. The partial roof canopy, covering roughly 2/3 of the spectator seating, will be assembled from large truss girders supported by perimeter columns drilled into reinforced caisson foundations. The trusses will extend inward and upward to support a lightweight roofing material made of tensioned PTFE or ETFE, allowing snow to slide off and sunlight to penetrate. Gutter systems along the edge of the canopy will direct meltwater to a network of heated downspouts connected to storm retention tanks. These tanks will be buried below the main entry plazas and will double as part of the site's sustainable stormwater strategy. MEP systems are distributed through a dual-zone layout, one handling fan-facing infrastructure such as restrooms, concessions, and suites, and the other servicing field operations, security, broadcast control, and food service logistics. The HVAC system uses rooftop air handlers with glycol loops and distributed VAV boxes. Energy efficiency is achieved through economizer controls, occupancy sensors, and energy recovery ventilation. All critical systems are backed by on-site diesel generators housed in hardened enclosures designed to withstand blizzard-level wind and snow loading. The playing field itself will be composed of a hybrid grass system layered above a heated concrete slab. This slab contains embedded tubing for hydronic field heating, which keeps the root zone warm even in sub-zero temperatures. Above that, laser-graded sand and organic root media support the grass surface, with perimeter trenches and high-speed pumps managing surface runoff. Access tunnels will allow maintenance vehicles and television equipment to move below the seating bowl without disrupting game day operations. Rather than beginning with infrastructure or shell work, the new Las Vegas Stadium, projected for completion in 2030, will start with the unique constraint of integrating into a tightly packed urban grid, adjacent to high-rise developments and hospitality venues. The pre-construction phase will involve extensive underground mapping, seismic zoning studies, and coordination with municipal transit systems. Because of the arid soil conditions and high potential for differential settlement, the site will undergo soil cement stabilization and the installation of moisture barriers before any structural excavation begins. The stadium's foundational system will rely on a dense grid of drilled piers extending deep into compacted desert substrata. These piers will support a post-tensioned concrete mat foundation designed to disperse vertical and lateral loads evenly across the uneven site. Embedded within this mat will be seismic base isolators, engineered to decouple the structure from ground movement in the event of an earthquake. Construction teams will stage equipment and materials using vertical lifts and a satellite laydown yard located several blocks away, minimizing disruption to nearby properties. Once below-grade systems are in place, vertical construction will begin with cast-in-place concrete cores that serve as the stadium's structural spines. Each of these cores will include fire-rated stairwells, elevator shafts, mechanical risers, and egress corridors. Simultaneously, the steel skeleton of the seating bowl will rise in a tiered sequence. Long-span trusses, fabricated off-site, will be lifted into position by lattice boom crawler cranes and temporarily braced using hydraulic shoring towers. These trusses will provide cantilevered support for luxury suites and upper-tier seating decks. The stadium's fully enclosed, climate-controlled roof will be a defining feature. Constructed from a combination of steel arches and a transparent ETFE membrane, the roof will span from end zone to end zone, supported by a pair of super trusses anchored into reinforced buttresses outside the main bowl. This roof will not only seal the stadium from the scorching desert climate, but also include operable louvers and shading fins that dynamically respond to solar intensity. A rooftop photovoltaic array will supplement the energy supply, integrated with a battery storage system located within a dedicated service vault. HVAC and power systems will be engineered to support the intense energy demands of a fully enclosed facility in the Mojave heat. Massive chilled water plants will operate on closed-loop systems, with thermal storage tanks allowing cooling operations to run during off-peak energy hours. Air distribution will utilize under-seat displacement vents in the seating areas and high-induction diffusers throughout the concourses. Electrical rooms will feature high-capacity switchgear, redundant transformers, and power conditioning systems to support lighting, broadcast, and emergency systems. The playing surface will be designed as a retractable, natural grass tray that can roll out onto an exterior service apron when not in use. This system allows the field to receive full sunlight and air circulation, preserving turf quality while minimizing indoor moisture accumulation. The rolling tray will glide on steel rails supported by hydraulic actuators and guided by laser sensors. By the final quarter of 2030, the stadium will be undergoing systems commissioning, staff onboarding, and final municipal inspections. The Las Vegas Stadium will then open its doors as one of the most technically advanced indoor venues in the world, tailored for year-round sporting and entertainment events in one of the most climate-challenging urban centers in North America. Instead of focusing first on structural systems, it's important to begin with the environmental remediation required for the Inter-Miami Freedom Park Stadium, expected to be completed in 2025. The site, a former municipal golf course with underlying contamination concerns, will undergo a thorough cleanup process before any building activity begins. This includes soil excavation, chemical stabilization, and the installation of vapor mitigation membranes to prevent any residual volatile compounds from entering occupied structures. Groundwater monitoring wells will be deployed around the perimeter during construction to track subsurface conditions in real time. Once environmental controls are in place, the next priority is site grading and drainage. The flat topography of the area demands an engineered solution for water management. Subsurface drainage basins and bioswales will be constructed throughout the property to capture and filter stormwater, routing excess into retention tanks placed beneath parking zones and service roads. These tanks are designed to handle the high rainfall intensity common in South Florida, with integrated pumping stations tied to the city's stormwater infrastructure. Foundational systems will vary slightly across the site, depending on load intensity and soil characteristics. The stadium itself will rest on a mat foundation supported by auger cast piles driven to refusal, while adjacent commercial and recreational structures may use shallow spread footings. The stadium's structural frame will consist of a composite steel and concrete system. Concrete cores will rise first, housing the elevator shafts and egress stairs, while structural steel beams and trusses will connect to these vertical elements, forming the primary load-bearing skeleton. The seating bowl is designed as a single-tier configuration with a steep pitch to create an intimate matchday experience. Precast concrete elements, risers, steps, and vomitories will be fabricated off-site and trucked in for sequential installation. Steel rakers and lateral bracing will provide support and rigidity. Integrated into the precast components will be electrical conduit and anchor points for seat mounting, lighting, and wireless access points. Above the stands, a sweeping roof canopy will stretch over the majority of the spectator area, constructed from lightweight, cantilevered trusses and covered with PTFE fabric. This canopy will serve both functional and aesthetic purposes, shielding fans from intense sun and tropical rain while contributing to the venue's architectural identity. Rainwater captured by the canopy will be channeled into edge-mounted gutters, then diverted into a reuse system to irrigate the stadium's landscaping. Unlike many large sports venues that prioritize vertical stacking, the forthcoming Centerville Bank Stadium, on track for completion in 2026, will adopt a horizontally integrated footprint with emphasis on ground-level connectivity and dispersed public access points. The site layout will feature low-profile transitions from parking zones and public transit drop-offs to the stadium perimeter, supported by a network of pedestrian bridges, landscaped entry plazas, and canopied walkways. Civil grading operations will be critical to shaping these zones, with laser-guided equipment used to achieve ADA-compliant slopes and integrated stormwater flow paths. Beneath the surface, foundational work will begin with test borings and load testing of precast concrete piles driven into glacial till and dense sands. These piles will support pile caps and reinforced slab-on-grade sections that form the structural base of the stadium's seating bowl and service levels. The superstructure will rely on a hybrid system: steel-framed decks and composite beams combined with cast-in-place concrete cores. Early trades will prioritize erection of vertical circulation shafts and mechanical risers, which anchor the building both structurally and functionally. The seating configuration will include dual primary tiers with an intermediate mezzanine level reserved for suites and club seating. The lower bowl will be partially recessed into the ground to enhance fan proximity to the field.